Hi everyone, I'm Changlin Li from Stanford. Today I present efficient training for human video generation with Entropy-Guided prioritized progressive learning. Joint work with collaborators across 5 institutions. In one sentence, our method customized large video diffusion models for human animation, achieving up to 2.2 times training speed up and 2 times 4 times GPU memory reduction, and improved generation quality. As you can see, it animates diverse references from paintings to anime to real people, with strong fidelity and pose adherence. Training human video diffusion models is extremely expensive. A DIT on 512x512 20-frame videos can consume 100 GB of VRAM. Conventional training updates all parameters every iteration, ignoring that not all parameters contribute equally. The plots below motivate our approach. Panel A shows freezing too many blocks hurts final FID, so capacity matters. Panels B and C shows that randomly skipping blocks sharply increases both loss and our CEI metric. And panel D shows the payoff. Training the 10 most important blocks converges much faster than training the 10 least important ones according to our CEI importance metric. This brings us to our first component, conditional entropy inflation, or CEI. The intuition is that a model adhering to a condition should show lower uncertainty after observing it. So for each block, we measure how much the conditional entropy inflates when that block is skipped. Assuming Gaussian outputs, this reduces to a simple log ratio of standard deviations, our training priority score pi b. We rank all blocks by pi b, so the most critical ones, shown in deep red, are unfrozen first. To verify CEI identifies the right blocks, we run a sanity check on SIT. Skipping the 3 highest CEI blocks collapses outputs into noise. Skipping the 3 lowest CEI blocks still gives clean samples. So higher CEI means more critical for conditional adherence, which means we prioritize for training. CEI tells us which blocks to unfreeze. Next, we decide how many. We define convergence efficiency as loss decreases per wall time. To estimate it, we use a nested diffusion supernet. At each stage, the supernet jointly trains across candidate and freezing sizes for one epoch. We then pick the candidate with the highest convergence efficiency and continue training. We reuse the supernet parameters so no compute is wasted. We evaluate on 3 datasets. On Bilibili, Entprog surpasses full training across all metrics. At 200k steps, we achieve a 2.2 times speedup and cut VRAM 1.6 times. The training curves below confirms given the same GPU hours, Entprog reaches better FID and other metrics. Qualitatively, you can see fewer artifacts and noticeable better facial details compared to the baseline defects highlighted in red. On TikTok and UBC fashion, Entprog achieves up to 1.7 times speedup, 2.4 times VRAM reduction, while maintaining or improving every generation metrics. Qualitatively, Entprog improves over fine-tuning baseline and reconstructs the reference subjects in all these cases. Our ablation confirms both components are independently effective. Removing the adaptive schedule gives the largest speedup but hurts FID-VID significantly. Removing CEI also degrades generation quality. Only the full Entprog achieves the best quality across nearly every metric while still delivering 1.52 speedup.